Hi everyone, thanks for tuning in to this symposium on philosophy and model theory. Before I started the talk, I just want to say a big thanks firstly to Tim Barton for organising the symposium, and secondly the people at ECAP 10. I think you guys have done a wonderful job organising what's an enormous online conference. So hope you enjoy the talk. So just to set up some nomenclature, there's two kinds of structures we often encounter in the literature or the philosophical literature at any rate. One is the idea of a particular structure. So these are structures whose exemplars are all isomorphic. So a good example here is the natural number 10 under the less than relation. But you might also think, lots of people think that the natural number structure is determined up to isomorphism, or at least definitional equivalence or something along those lines. General structures, by contrast, are those that have many non-isomorphic exemplars. So the canonical example here is the group structure. You can have the group of rotations on the triangle, but I can also look at the group of integers. One of those is infinite and one of those is finite. These are highly non-isomorphic objects. Okay, and then corresponding to this distinction of particular and general, we have non-algebraic and algebraic theories. So the non-algebraic theories are precisely those that refer to particular structures, and algebraic theories are those that correspond to general structures. Now, if you're going to have general structures, you have to have incomplete structures. So structures that do not determine all the properties satisfied by their instantiations, or all the structural properties in some sense satisfied by their instantiations. As I just mentioned, you can have the group of rotations on the triangle and the group of integers, and those are very, very different kinds of particular structure. So Barton and Walsh, as we'll see in a minute, seem to suggest that this idea of an incomplete structure, the kind of general structures, are difficult to understand. And instead we should think of general structures at the level of theories that apply to multiple different particular structures. So rather than a claim about the existence of particular structures, they want to countenance general structures as just particular kinds of theory, algebraic theories that apply to multiple different particular structures. Okay, so with this in hand, I just want to introduce my main claim. I'm going to argue that the idea of an incomplete structure, a single structure with multiple different non-isomorphic instantiations, this is indeed a difficult to understand concept, but we at least have some reasons to accept the existence of these structures. I'll do this in three sections. Firstly, I'll talk about intentionally and unintentionally general structures. I'll then talk about what I call Lego-like structures. And finally, I'll conclude with some questions for Tim and Sean. Okay, so in lots of areas of mathematics, we have full categoricity results. Examples here include arithmetic and the reals, but for set theory, things are a little more complicated. So here we only have quasi-categoricity. So this means that if we have two models, M1 and M2, either they're isomorphic to one another, or M1 is isomorphic to a proper initial segment of M2, or M2 is isomorphic to a proper initial segment of M1. Now, given this quasi-categoricity result, there's a sort of philosophical question of how we interpret the result. And one option, and this has been proposed by Dan Isaacson, is that second order ZFC defines a single particular structure, but it's incomplete in some sense. So there's just one structure there, but properties of it may be indeterminate. So for instance, unbounded statements like the generalized continuum hypothesis or certain large cardinals may be indeterminate. Now, regarding this idea of incomplete structures, Barton and Walsh seem fairly unwilling to countenance the idea of them. So this is them in their book. None of this forces us to follow Isaacson in holding that our quasi-categorical set theory describes a single but incomplete structure. We can equally hold that second-order ZFC is an inevitably incomplete axiomatization, which applies to many different complete structures. To our ears, at least, this is somewhat easier to understand than the idea of an incomplete entity. Good, so I agree with Tim and Sean that the idea of a single structure with indeterminate properties is hard to understand. But perhaps we want to countenance them anyway. Perhaps this is worth it. So a different example, recently I looked at the idea that since set theory could develop legitimately in mutually incompatible ways, we shouldn't accept that there's a single structure with determinate properties that we've isolated. So nonetheless, perhaps this quasi-categoricity theorem And indeed, the internal versions that can be done proof theoretically that Tim and Sean look at in their book should convince us that we intend to talk about a single structure, even if we don't. So here's an example. It's in a slightly different vein to the quasi-categoricity theorem. Suppose that we think that there are at least two legitimate futures for set theory, one in which the proper forcing axiom holds and hence not CH, and one in which ultimate L is true and hence CH is true in this world. Well, perhaps, given this, we should think that CH is indeterminate. There are legitimate futures in which CH is true and legitimate futures in which CH is false. So we'd now be in a position where we think that our discourse about sets determines a single structure, because after all, we have these quasi-categoricity results, both internal and semantic. As a matter of fact, though, our thought about CH is indeterminate. This is witnessed by the fact there are different possible futures, where in one CH is true, and in one we select an axiomatization in which CH is false. Now, a natural way to make sense of this would be to hold that our discourse and thought talks about a single incomplete structure. It doesn't determine all of its properties, in particular CH. And insisting that our thought does not determine a single structure fails to take into account the success of ZFC2 as an axiomatization and the fact that we have these quasi-categoricity theorems. And insisting instead that we do talk about a single structure with determinate properties, that would give us the conclusion that one of these futures is illegitimate, which perhaps we don't want to countenance. Well, this is a controversial argument, but if you accept it, then perhaps you think that there's an axiomatization and structure which doesn't determine CH, but on which the reals are determinate and the universe is transitive. Maybe that should be what underlies our thought. So this could be done in something called ZFC in quasi-weak second-order logic. I'm not going to go into it too much. Basically, you let the second-order variables include all countable relations, and in this version of ZFC in quasi-weak second-order logic, you can determine the reals up to isomorphism, but CH can vary between different models. Okay, now suppose we look at our intellectual descendants, and they have settled on a particular canonical theory of sets that settles CH. Now, they might look at us, look at our predecessors and say, look, the structure of our intellectual ancestors, let's say it happens to be actually given by ZFC in quasi-weak second-order logic, is a substructure of our structure given by ZFC2, or second-order ZFC. So there seems to be a sense in which we can say true things, or at least our intellectual descendants can say true things about how indeterminate or incomplete structures relate to complete structures, for instance, or at least quasi-complete structures. And it bears mentioning as well that some work has been done in making sense of this notion of an indeterminate structure. So Chris Gambler has a recent paper that does this, though it does in something of a different direction with a different axiomatization. So maybe then we should accept the existence of incomplete structures. We can still retain the algebraic sense of the various parts of our discourse, even if we think there is also an incomplete structure. So the slogan here, let 1,000 model theoretic flowers bloom. Good, so that's one way in which you might think there's pressure to accept the existence of incomplete structures, when we intend to talk about a particular structure, but perhaps we fail for some reason. However, the theories in question we might look at here, so things like set theory, are often incomplete in the sense that for something in the language of the relevant structure, there are models in which that sentence holds and models in which it's false. Okay, but now I want to move on and look at a situation in which we also get a sense of incomplete structures, but for complete theories. Right, now, here's the informal philosophical definition I'm going to work with. So we say that a structure is Lego-like if it has a template structure. Now you can, at the base, you can think of these as your Lego blocks, possibly in an initial configuration. And secondly, a method of building unique up to isomorphism models from the template. You can think of this as your instruction leaflet for your Lego kit. And I'm going to say a theory or discourse is Lego-like if it axiomatizes a Lego-like structure. Good. So that's very informal and philosophical, and a substantial question is exactly how we make this formal. And this can be done using developments in model theory since about the 1960s. So the key notions are going to be strong minimality and the notion of a pre-geometry. So you've got the definition of what a pre-geometry is on the slide. It's roughly speaking, it's a set, and there's a closure operator from the power set of that set to the power set of that set. And I won't go through the axioms, but roughly speaking, they capture the notion of algebraic closure, or closure as you would find it in, for instance, the theory of fields. Right, so with this idea of a pre-geometry in hand, you can come up with various notions closely related to the idea of a vector space. So, for instance, you can define what it is for a set to be independent, you can define what it is for a set to be closed, but in particular, you can also define what it is for a set to have a basis and come up with, and this is very important, a particular notion of dimension. And you can think of this notion of dimension as the number of coordinates you need to specify a particular point in the space. So this is a kind of model theoretic generalization of some definitions that you get in other parts of mathematics. Okay, now for the second component. So let's take a model of some complete theory T with universe M and assume that T has infinite models. And then we look at the tuples in M that satisfy some particular formula phi, right? That's this definition here. Now, this set is minimal if for all formulas in the language of the model, if you took at the intersection with other formulas, you get something that's either finite or cofinite, okay? And now we say that a formula is strongly minimal if this formula defines a minimal set in every elementary extension of M, and a theory T is strongly minimal if the equality formula itself is strongly minimal. So now if we take some strongly minimal set G, this is going to be defined using parameters from some finite subset, right? And then you can define a closure operator by looking at the particular set unioned with this finite set of parameters and intersected with your strongly minimal set. Okay, now using the model theoretic notion of algebraic closure, you can get out of this a particular pre-geometry, namely this initial strongly minimal set you started with the closure operator defined as up here. Okay, so that's all very quick and a lot of technical material, but I'm going to claim, and I think there's a lot more work to be done here, that you can think of a strongly minimal set as our template for a Lego-like structure, and the corresponding pre-geometry is our instruction manual, right? So your strongly minimal set is providing you your initial starting conditions, let's say, and then the pre-geometry in question is telling you how to combine over a particular base this strongly minimal set to obtain something that is isomorphic in a particular cardinal. This is witnessed by the fact that strongly minimal theories are categorical in every uncountable power. So in picture form, you have the basis for your model that you want to construct. You have your strongly minimal set, and then what is going to happen is that your closure operator is going to tell you how to combine this strongly minimal set in order to yield something that is determinate. Okay, good. So that's somewhat technical, but assuming that can be made out, there are then apparently true things that we can say about these structures. So for instance, the trivial infinite structure, so this is the structure that just consists of a pure cardinality with no relations on the points, is a substructure of every Lego-like structure. Now I make no claim about the bases here. This is just a claim purely about the incomplete structures. I don't tell you how far or how the size of the model, but I have a particular pattern in some sense, and I have a way of, from this initial strongly minimal set, constructing my model. Okay, so for all I've said thus far, that there are ways of saying true things about apparently incomplete structures, this could all be paraphrased in terms of theories. So I could say, for instance, given my Lego-like structure of the pure cardinality structure and another Lego-like structure, if I have two models of the same cardinality, one can be embedded into the other. So this can be paraphrased away, but perhaps the more natural paraphrase is to just admit incomplete structures. Okay, so for instance, it's more natural if you have some incomplete structures to look at substructure relations or embed them into one another without having to go through a paraphrase that depends on the theories, right? So again, in slogan form, let 1,000 model theoretic flowers bloom. You can still have the Barton and Walsh way of looking at things, but you could also admit, by admitting incomplete structures, perhaps you would come to some nice mathematical insights or come up with some nice mathematical tools. Okay, so here's two questions that I'd love to hear people's thoughts on. The first is, are there significant objections to the idea of incomplete structures beyond the fact that, as Sean and Tim correctly identify, they're a little hard to understand in some sense, but are there really significant problems that we can come up with philosophically speaking? The second question is very closely related. How significant are these possible advantages of admitting incomplete structures? So if I admit incomplete structures, do I suddenly obtain a whole bunch of mathematical insight? If that's the case, then that would be a strong point in their favor. Right, so given those questions about the advantages or disadvantages of a theory of incomplete structures, a third question that I'd very much be keen to hear people's thoughts on is, if you accept a theory of incomplete structures, what are the particular prospects for developing such a theory? So, what kinds of theories of incomplete structures can we come up with, and how do they function? A final question that's maybe slightly tangential, but nonetheless I would love an answer to, is that, as Barton and Walsh note, these classification results that I've mentioned and more besides, we can talk about Morley categoricity and things like that, have largely been ignored by philosophers. And I'd be really interested to hear if people have an opinion on why this has been. Is it a merely sociological fact, or is there a very deep reason as to why these are not philosophically relevant, or are they philosophically relevant? Okay, so with those questions in hand, I think it's time to open it up to the discussion. I'm hugely grateful to a number of people who you can see on the slide, and I'm really looking forward to talking to everyone about these issues.